All right, so let's talk about something called equilibrium tables. Your book or different sources that you are using may refer to these as either ICE tables or RICE tables, and I will show you why this is. So we use an equilibrium table to determine concentrations of reactants and products during different parts of a chemical reaction. So I'm just going to write one of these out and kind of explain it as we go. So it goes R-I-C-E down the side, and R stands for reaction. I stands for initial. C stands for change. And E stands for equilibrium. Okay, so the best way to go through and teach this is to just use an example. So I'm going to write out the example and then we'll work through the equilibrium table. So here's the problem. It says, when heated, phosphorus pentachloride forms phosphorus trichloride and chlorine gas. It says when 1.00 moles of phosphorus pentachloride is allowed to come to equilibrium, in a 1.00 liter container, the mixture is found to contain 0.135 moles of phosphorus trichloride. What is the molar composition at equilibrium? And what is the Kc? Okay, so a lot of information here. So let's just go through and see what we have and how we're going to use this table to solve this problem. So first we're going to write the reaction from the word problem. So it says we have phosphorus pentachloride and it forms phosphorus trichloride and oxygen gas. So phosphorus pentachloride is PCl5, and it forms phosphorus trichloride, PCl3, and oxygen gas, which we know oxygen is one of the diatomic molecules, so oxygen gas is oxygen. All of these are gases. You can assume that all of these are gases for this equilibrium chapter. Okay, so that's the first part. We've written R in our equilibrium table. This is the reaction. Again, always make sure that your chemical reaction is balanced, which this one is. I have one phosphorus on either side, and I have, oh, sorry. This should not say oxygen gas. Sorry. This should say chlorine gas. Sorry, wrong problem. Cl2. Also diatomic. So I have 1 phosphorus on each side, and I have 5 chlorines on each side. Okay, so now let's see what other information is in here. So it says when 1 mole of phosphorus pentachloride is allowed to come to equilibrium in a 1 liter container, the mixture is found to contain 0.135 moles of phosphorus trichloride. So there's some important information here. It says when 1 mole of phosphorus pentachloride is allowed to come to equilibrium. So that means this is the amount before equilibrium. That means this 1 mole in 1 liter, so 1.00 molar, is the initial concentration. This is the initial concentration. So that's what goes here. We have 1.00 molar initial concentration of the PCl5, the phosphorus pentachloride. Concentrations in molarity are what go in these equilibrium tables. So we have a 1 liter container, so moles per liter is molarity. So the number of moles also happens to equal the molarity in this case because the volume of the container is 1 liter. So remember, when we start a chemical reaction, we start with an initial concentration of reactants. We do not start with an initial concentration of the products unless it is otherwise specified. Unless it tells you we are initially starting with concentrations of reactants and products, you can always assume that you start a chemical reaction with a concentration of reactants, but no products have been produced yet at the start of the chemical reaction. So that's how you get the initial concentrations. It will say it's before equilibrium. So it says when 1 mole of phosphorus pentachloride is allowed to come to equilibrium, the mixture is found to contain 0.135 moles of phosphorus trichloride. So this is after we have been allowed to come to equilibrium. This 0.135 moles in 1 liter, this is the equilibrium concentration of the phosphorus trichloride. So here's phosphorus trichloride. You could make this into a table just so it's easier to see what's happening here. So the equilibrium concentration of the phosphorus trichloride is 0.135. And then it says, what is the molar composition at equilibrium? So the molar composition at equilibrium, what this means is, what is the concentration of everything at equilibrium? So I'm just going to write down here PCl5, and then I'm going to write down here EQ, because that's the concentration at equilibrium. What is that? What is the concentration of the phosphorus trichloride at equilibrium? Well, they tell us that in the problem, 0.135 molar. And then what is the concentration of the chlorine at equilibrium? So that's what this means. What is the molar composition at equilibrium? It means what is the molar composition of everything that's in that reaction. And then what is the Kc? Because remember, the Kc is the concentration of the products at equilibrium over the concentration of the reactants at equilibrium. So we can use this bottom line right here to solve for the Kc once we've used this table to determine what the equilibrium concentrations are. So the way we do this is, this table works because we're seeing what the change is. So for the change is always negative for the reactants, because the concentration of the reactants, once this reaction starts, is always decreasing. So the change is going to be a negative amount. The concentration for the products, as this reaction proceeds, it's starting at 0, it's always going to be increasing. So the change is going to be a positive amount. So if we go all the way back to our very first lecture about this, so this is essentially what we're doing. Here are the initial concentrations, and we're trying to solve for these equilibrium concentrations. So at the beginning of this reaction, it doesn't matter what the actual equation here, they all kind of follow this same pattern. So at the start of this chemical reaction, we have some amount of reactants, and as we reach equilibrium, the amount of reactants that we have decreases. So this is going to be a negative change because the concentration is decreasing over time from initial to equilibrium. The opposite is true for the products. Again, this is not specific to this reaction. This happens for all reactions in equilibrium. We initially start out with no products. So over time, as we reach equilibrium, the change in the concentration of products is going to increase. So the amount by which this change is X. So the concentration of the reactants, it's always going to be minus X, and X is based on the coefficient of that species. So for example, this phosphorus pentachloride, I have 1 mole of it. So the amount of change between initial and equilibrium is going to be minus X. 1X, because I have 1 mole of phosphorus pentachloride. So now let's look over here. As a product, the amount of change between initial and equilibrium is going to be plus 1X. And now the amount of chlorine gas between initial and equilibrium is also going to be plus 1X. So now this is kind of like a little puzzle that we can solve to get the equilibrium concentrations for everything. Because remember, that's the first thing that we're solving for, is what is the molar composition? The molar composition is the concentration at equilibrium of everything. So now what we do is we're going to bring everything down to this equilibrium row. So I'm going to add these together. So I have 1.00 minus X. Here I already have the amount. Now here I have 0 plus X, so it's just X. So you can do this however you want, but if you think about what's happening here, in this example, I have 0 initially, plus X is 0.135. So in this equilibrium table, I am able to determine that from this 0 plus X equals 0.135. So that means X must equal 0.135. So if that means if the equilibrium concentration of PCl5 is 1 minus X, it must be 1.00 minus 0.135, which is 0.865. So that means 0.865 must be the equilibrium concentration of my phosphorus pentachloride. So here, if 0 plus X equals X, and I said X is 0.135, that means the concentration of chlorine must also be 0.135 molar. So now I've solved the first part of the problem by using this equilibrium table. I used the information that was given to me to determine what X is, and then I applied that to this bottom row to solve for the equilibrium concentrations of the reactants and the products. So that was the first part. What is the molar composition at equilibrium? 0.865 molar PCl5, 0.135 molar PCl3, 0.135 Cl2. So that's the first step. The next step is what is the Kc? So whenever you're using the Kc, you are using the product and reactant concentrations at equilibrium. This is the row of the table that you want when you're talking about solving for the Kc. Only the equilibrium concentrations, which we've solved for down here. So I'm going to say Kc equals the concentrations of the products at equilibrium. Remember, all our same rules apply. Coefficients become exponents. pure substances are excluded. Okay, so we don't have to worry about any of that because these are all gases. And they all have a coefficient of 1, so nothing extra happening here. So concentration of the products, I'm just going to write it out. I'm going to write PCl3 times the concentration of chlorine gas, Cl2, over the concentration of PCl5, the phosphorus pentachloride. That's going to give me my Kc. I'm going to solve for that actual number by plugging in the equilibrium concentrations that I solved for. Again, it is very important that you understand the values that go in this for the Kc are always the equilibrium concentrations, never the initial concentrations. Remember, Kc tells us the position of equilibrium, so we only want the concentrations at equilibrium. So I'll write this again. Kc, PCl3, 0.135 molar, times chlorine, 0.135 molar, over the concentration of the phosphorus pentachloride, 0.865. And again, also always remember that these are concentrations in molarity. That's what goes in the Kc. That's why it's important that everything that goes in your equilibrium table is concentrations in molarity. So now let's solve for this. I'm going to say 0.135 times 0.135, that's my numerator, divided by my denominator, 0.865, gives me about 0.021069, whatever. So now I'm looking back at the problem to see how many significant figures my answer should have. So everything in this problem has 3 significant figures. Since I'm dealing with multiplication and division, my answer should also have 3 significant figures. So I would say, with correct rounding, 0.0211, because this 0.0210, the next number to the right is greater than 5, so I would round that up to a 1. So I would say 0.0211, that is the Kc. Remember, the Kc is a ratio of products to reactants at equilibrium. It does not have a unit. So this is an example of how we use equilibrium tables to solve for molar concentrations at equilibrium and then use those molar concentrations at equilibrium to solve for the Kc. We are going to be applying this technique of using equilibrium tables to almost everything else in the rest of this course. When we start talking about acids and bases and solubility, the chemistry will change, but the technique that we use to solve for concentrations at equilibrium will be the same. So it's very important that you feel comfortable using equilibrium tables because we will use them a lot the rest of this quarter. I'm going to post more videos of examples, different chemical reactions, different examples using equilibrium tables. This is the way that your book shows it, so this is the way that I will teach it. If you see this explained a different way, feel free to use the technique that makes the most sense to you. I'm never grading the way that you show your work. You will need to show your work so that it makes sense as to how you arrived at your answer, but you don't have to do it the same way that I do it. But here are equilibrium tables, and I will post more examples after.